And now we will go to some examples. The first one is, using the ideal gas law, calculate ZA0 and FA0. A gas of pure A at 830 kilopascals, which are 8.2 atmospheres, enters a reactor with a volumetric flow rate V0 of 2 cubic decimeters per second or 2 liters per second at 500 K. Calculate the entering concentration of A, which is ZA0, and the entering molar flow rate FA0. Solution. We recall that for an ideal gas, CA0 is equal to PA0 divided by RT0, which is equal to YA0 times P0 divided by RT0, where P0 is the initial pressure at time t, which is 830 kilopascals. Yx0 is the mole fraction and is equal to 1 because only A is entering the reactor, so pure A is inside the reactor, so the mole fraction is 1. T0 is the initial temperature, 500 degrees Kelvin, and R is the gas content, 8.314 liters kilopascal divided by mole Kelvin. If we substitute these parameters into the equation, we will come that ZA0 is equal to 830 kilopascals divided by 3.14 liters kilopascal divided by mole Kelvin times 500 Kelvin, which will give us a result of 0.2 moles per liter. We could also calculate the partial pressure in terms of concentration by the equation PA0 equals CA0 divided by RT0. But since only pure A is entering the reactor, the total pressure and partial pressure are the same. Now, the entering molar flow rate FA0 is just the product of the entering concentration CA0 and the entering volumetric flow rate V0. So, FA0 is equal to CA0 times V0, which is equal to 0.2 moles per liter times 2 liters per second, which will give us that a result of FA0 equals 0.4 moles per second. This feed rate of 0.4 moles per second is in the range of what is necessary to form several million pounds of product per year, and we are going to use this molar flow rate in different problems later on. Example 2. Sizing a CSTR. The reaction described by the data in a table given in the next pages is for a reaction where A goes to B. And this one is going to be carried out in a CSTR. Species A entered the reactor at a molar flow rate of 0.4 moles per second. A. Using the data in the table given in the next page, calculate the volume necessary to achieve 80% conversion in a CSTR. B. Shade the area in figure 2.2 that will give the CSTR volume necessary to achieve 80% conversion. And here we have the table we have 4 rows. In the first row, we have the conversion x that goes from 0.0 to 0.8. In the second row, we have the rate in moles per cubic meter second, which goes at 0.0 conversion, the rate is 0.45, and at 0.8 conversion, the rate is 0.05. And then the next row is 1 divided by the rate, which is 2.22 when x equals 0.0, and 20 when x equals 0.8. And the last row is FA0 divided by minus RA, which is 0.89 when x equals 0, and is 8 when x equals 0.8. If we plot the values of FA0 divided by minus RA as a function of x, which these values are given in the table that we just described, we can obtain the plot shown in the figure 2.2. So, in the vertical axis, FA0 divided minus RA, and in the horizontal axis is the conversion x. And this is a Levenspiel plot, which we are going to see is very used in the next problems. So, solutions. The equation below gives the volume of a CSTR as a function of FA0, x, and minus RA, which is the volume is equal to FA0 times x divided by minus RA at the exit. In a CSTR, the composition, temperature, and conversion of the effluent stream are identical to that of the fluid within the reactor because perfect mixing is assumed. Therefore, we need to find the value of minus RA, or the reciprocal, at x equals 0.8. If we go to the table, we will see that 1 divided by minus RA when x equals 0.8 is equal to 20 cubic meters second divided by mole. Now, if we substitute this value into the equation defining the volume for an entering molar flow rate of 0.4 moles of A per second and a conversion of x equals 0.8, that will give us that the volume is 0.4, which is FA0, times 1 divided by minus RA, which is 20 cubic meters second per mole, times the conversion, which is 0.8, and we will have a result of the volume 6,400 liters. Now, let's shade the area in the figure 2.2 that yield the CSTR volume. If we rearrange the equation defining the volume, we will have that the volume B is equal to FA0 divided by minus RA times x. In the figure E2/2 the volume is equal to the area of a rectangle with a height of FA0 divided by minus RA, which is 8 cubic meters, and a base of x equals 0.8. So this rectangle is shaded in the figure that we are going to see later on, but his volume is the height times the base, which is 8 times 0.8, and So the volume is 6.4 cubic meters, which is the same result that we obtained in the problem number 1. And here we have the CSTR volume necessary to achieve 80% conversion is 6.4 cubic meter when it's operated at 500 Kelvin, 830 kilopascal, and with an entering molar flow rate of 0.4 moles per second. This volume corresponds to a reactor about 1.5 meters in diameter and 3.6 meters high. So here in the Levenspiel plot that we have here, we can see that the shaded area is the total volume of the reactor, and this shaded area is the multiplication of Fa0 divided by minus Ra, which is in the vertical axis and is 8, and the conversion x, which is in the horizontal axis and is equal to 0.8. So 8 times 0.8 is equal to 6.5 cubic meters.